Hello everyone, this is Dhanalakshmi, Assistant Professor from Triply Department of R&D Engineering College, and I welcome you all for this video. In this video, I would like to discuss about Thevenin's theorem, which is the very important theorem in our circuit analysis. Whenever we do any analysis in the circuits and networks, so the major theorems where what we have is Thevenin's, Norton's, superposition. So where across all those many theorems are there. So out of that, this Thevenin's theorem is most important. Where we will try to discuss those this theorem in this video. And let me go to the presentation. Thevenin's theorem, as we know that many theorems have been stated for circuit analysis, and one among that is going to be our Thevenin's theorem, and this is a very important theorem. So whenever people begin with the circuit analysis, they are in a position to know about this Thevenin's theorem. So in this Thevenin's theorem, let me go to the statement, the theorem statement, then we can proceed with the things, how to solve that, and how do we have to reduce any network given to us into a single equivalent voltage source. So Thevenin's theorem. So the statement, it seems to be big, but it's a very simple logic where Thevenin's theorem states that any two-terminal linear network that is having a number of voltage and current sources and also the resistances can be replaced into a single voltage source in series with the resistance. So this is the idea of Thevenin's. So it states that any network, any two-terminal linear network, how big it is, so that network which is consisting of n number of voltage and current sources and also the resistances, all that can be replaced by a single voltage source in series with the resistance. And that single voltage source is going to be our open circuit voltage across the terminals, and that is what we call it as Thevenin voltage. And the equivalent resistance of that network is going to be our Thevenin resistance. So as the theorem, from the statement of theorem, we can understand that any network, two-terminal linear network, can be reduced into a single voltage source in series with the resistance. So we'll take an example and we'll try to solve it so that we can understand it better. So let me take a simple circuit here. So here you can see a simple circuit. One second, let me go to the pointer. So here we have taken a simple circuit where you can see it's a circuit where consisting of two loops here. So now for time being, let us assume that, or let me assume that this 24 ohm branch is going to be my load resistor. Right? So that is the idea here is I want to find out what is the current flowing in this 24 ohm branch using Thevenin's theorem. So whenever the branch wherever I want to find out the current or wherever I want to find out the voltage, that branch or that element I'll be taking as the load element. So load resistance here I'll be taking this 24 ohm has to be the load resistance, or this branch will be the load branch. Now for applying this Thevenin's theorem, what we have to do is first we have to identify at which branch or the element we are going to find out the equivalent, across which branch or the element we are going to find out the equivalent, we have to identify first. So here the 24 ohm is going to be the load resistance. So our first step is, in order to get the Thevenin's circuit, we have to remove this load branch and we have to make that terminal to be open. So that is the idea here is this big network or any network, that is here this network or this circuit is going to be reduced like this. So what we are going to do is we are going to reduce this circuit or network into a single voltage source with a resistance in series with that. So this is what called as the Thevenin's equivalent circuit. So this portion is our Thevenin's equivalent circuit, which is consisting of a single voltage source in series with the resistance. So that is any network or any linear circuit can be reduced into a single voltage source in series with a resistance. That is the idea of Thevenin's. So this is our Thevenin's equivalent. So now here the idea is that we want to know how to find out the Thevenin voltage as well as the Thevenin resistance. Now we'll see how to find out the Thevenin voltage and Thevenin resistance. So for that, what we have to do is we have to identify our load resistance. Here the load resistance is going to be 24 ohm, because where in this 24 ohm only we are going to find out the current flowing. Right? So the idea here is the intention is to find what is the current flowing in 24 ohm branch with the help of Thevenin's theorem. First step, we have to remove this 24 ohm and we have to make the terminals to be open. So let the terminal be A and B. So I'm marking the terminals to be A here and here the terminal to be B. So after removing the 24 ohm, I'm going to make this terminal to be open. So this is how we got the circuit. So here see, so you can see in the circuit, you can see in the diagram that where this is the point where we had our, so this is the point where we had our 24 ohm branch and we removed that 24 ohm branch and we mark the terminals to be A and B. So we mark the terminals as A and B and now we want to find out what is the voltage across this A and B. So we want to find out what is the voltage across A and B, and this voltage across A and B, that is VAB, is nothing but our Thevenin voltage VTH. Right? This open circuit voltage, that is the open circuit voltage across the terminal A and B, is going to be our Thevenin voltage VTH. Right now, when we observe the circuit, we came to know that if you want to get the voltage across this terminal A and B, this is nothing but the voltage across 12 ohm, because we know that in parallel the voltages are same. So therefore, whatever voltage we have across this 12 ohm branch is going to be equal to the voltage across this VAB, because in parallel the voltages are same. So therefore, we can came to a conclusion that the whatever voltage is there across this 12 ohm will be the voltage across VAB. Or I can say that V12 is the voltage across this 12 ohm is going to be equal to VAB, and this VAB is equals to our Thevenin voltage VTH. Yes. So our idea here is to find the voltage across 12 ohm. So when we see this circuit again, so from this 10 volt, the 10 volt source, the current will be raising, and here you can see that here we have another resistor 2 ohm, and we can see that this 2 ohm and this 12 ohm both are connected in series. Both this 2 ohm and 12 ohm are connected in series. Why? Because the current from the 10 volt source, the current I from the 10 volt source is going to flow into this 2 ohm, as well as the same current, whatever current that flows in 2 ohm is the current that is going to flow in this 12 ohm also. Whatever we know that in series the current is same. Right. So here we can conclude that this 2 ohm and 12 ohm are connected in series, because whatever current that flows in 2 ohm is going to flow in the 12 ohm also. So therefore, the current I, whatever it comes here, is going to flow inside this 12 ohm, because here current cannot flow, because here it is the open terminal. A is the open terminal where current cannot flow. So the entire current that whatever current that comes from the voltage source, 10 volt source, will be flowing into 2 ohm, and the same current is going to flow into the 12 ohm. So therefore, we can say that this 2 ohm and 12 ohm are in series. Now in series circuit, what we can do is now our intention is to find what is the voltage across this 12 ohm. So we want to find out what is V12. That is, our intention is to find the V12. In order to find this V12, we can apply the voltage division rule. Right? And I hope that you know voltage division rule. So whenever we want to find out the voltage in a series circuit, because now this is a series circuit where 2 and 12 are connected in series. So in order to find the voltage across 12 ohm, we can apply voltage division rule. So therefore, when we want to find out the voltage division rule, so what is the formula will be total voltage. So now our intention is to find the voltage across 12 ohm. So therefore, V12 we are going to find out using the voltage division rule. So voltage division rule, we know that it is total voltage. Here the total voltage is going to be 10 volt. Here the total voltage is 10 volt. So therefore 10 and into the resistance at where we want to find out the voltage. So out of this 2 and 12, we want to find out the voltage across 12 ohm. So therefore the resistance at which you want to find out the voltage, that resistance. So 12 divided by the total resistance, where the total resistance here will be 2 plus 12. That is 2 plus 12 will be the total resistance. So therefore it will become, when you calculate these values, you will get it as 8.57. That is 10 into 12 by, that is what I have written here, 10 into 12 by 14. So this we got it from the voltage division rule, and when we calculate, this value will become equal to 8.57 volts. So therefore, in order to find the voltage across 12 ohm, what we can do is we can use the voltage division rule, where when we apply the voltage division rule, we know the formula that the total voltage into the resistance at where you want to find out the voltage divided by the total resistance. So 12 is the resistance where we want to find out the voltage. So therefore 10 into 12 by 2 plus 10. So that is 10 into 12 by 14 will give you 8.57 volts. And this is nothing but our Thevenin voltage VTH, because Thevenin voltage is the open circuit voltage across the terminal AB, right? So Thevenin voltage is nothing but the voltage across, it is the open circuit voltage across the terminal A and B, where this open circuit voltage AB, VAB is nothing but the voltage across 12 ohm, because parallel to that is the 12 ohm resistor. So we know that in parallel the voltages are same. So it is enough to find the voltage across 12 ohm, that gives you the voltage across VAB, and that is nothing but our Thevenin voltage. So we got our Thevenin voltage to be 8.57 volt. So this is our first step, that is to find the open circuit voltage across the terminal AB. So that is our Thevenin voltage. And the second step will be to find the Thevenin resistance. So in order to find the Thevenin resistance, let me go back to the original circuit. So this is the circuit given to us. Again go back to the original circuit and again remove the load resistor. So here the load resistor is going to be the 24 ohm. So we are going to remove that 24 ohm, and also after removing that 24 ohm, just keep the terminal AB open, right? Just keep the terminal AB open and just see the remaining portion of the circuit. In the remaining portion of the circuit, wherever we have the voltage source and the current source, all those sources have to be removed. So in while removing that voltage source, that portion should be made short circuit, and while removing the current source, that portion should be made open. So voltage source, when we are going to remove it, that has to be replaced by a short circuit, and when we are going to remove the current source, that place have to be replaced by open circuit. So that is what we have done here. So after removing this load resistor, when we see the remaining portion of the circuit, here we can see that 10 volt source is there. So therefore, we have to remove this 10 volt source. In order to, after removing the 10 volt source, we have to replace it by a short circuit because that is a voltage source. So that is how we are getting this circuit actually. So this circuit is to find the Thevenin resistance. So where you can see that here we had the 24 ohm branch. So we removed the 24 ohm load resistor branch. And after removing that load resistor, we have to look the circuit. And in that circuit, wherever we have sources, all those sources have to be removed. So here, if you see that here we can have, you can see a 10 volt source is available, and that 10 volt source we removed, right? We removed that 10 volt source, and that is replaced by a short circuit. That is replaced by a short circuit. Second. So that is replaced by a short circuit. So therefore, after removing the sources and since it is a voltage source, we replace that by a short circuit, and now we got the circuit like this. So if you see, and again we want to find out the Thevenin resistance across from the terminal. We are going to look the circuit from the terminal AB. That is, we are going to look the circuit from the terminal AB. That is, we are looking from this point. So when we look from this point, we have to solve the resistance from the other end, this end. So therefore, when we try to solve from the other end, and when you see the circuit, this becomes a very simple circuit where you can see that this 2 ohm and the 12 ohm both are connected in parallel. This 2 ohm and 12 ohm both are connected in parallel, and thus we can use the formula for resistances in parallel. So now you can see that both this 2 ohm and 12 ohm are connected in parallel. We know that in parallel, the starting node of resistors and the ending node of resistors should be same. And then if it is so, then we can say those resistors are connected in parallel. So here you can see that 2 ohm and 12 ohm are exactly connected in parallel. So therefore, we can use the parallel resistance formula. So when we take the parallel resistance formula, and we know the formula that it is R1 R2 by R1 plus R2. So therefore, the equivalent resistance will be R1, this is 12 into R2, that is 2 divided by the total resistance R1 plus R2. So that becomes 14. So the formula for equivalent resistance will be R1 R2 by R1 plus R2. So that gives you 1.71 ohms. So the resistance in parallel will be calculated by using this resistance in parallel formula. That is, the formula will be R1 R2 by R1 plus R2. This we know already, so I'm not just not mentioned here, but anyway I'll mention it now. So R1 R2 by R1 plus R2. Using this formula, we can calculate the resistances in parallel. So here you can see that after calculating, we are getting that value to be 1.71 ohms. So this is how we have to calculate the Thevenin resistance. And after calculating the Thevenin resistance, already we calculated the Thevenin voltage. Now we have to frame the Thevenin's equivalent circuit. So actually, this is our original circuit given. This is the original circuit given, where we are going to convert this circuit into a Thevenin's equivalent circuit. So when we say Thevenin's equivalent circuit, which will be consisting of a voltage source along with that resistance in series. So this voltage source is what called as Thevenin voltage, and this resistance in series is what called as the Thevenin's resistance. So just now we calculated the Thevenin voltage, which is 8.57, and Thevenin resistance, which is 1.71. So now what we did is, here the idea is we replace this entire network or circuit into a single voltage source which is having a resistance in series. So this is our Thevenin's equivalent circuit. So like this, any circuit or any network can be, any linear two-terminal network can be reduced into a single voltage source in series with the resistance. So this is the idea of Thevenin's. And once we got the Thevenin's equivalent circuit, now we can connect back the load resistance. So initially we removed this load resistance. Now you can connect back this load resistance, that is 24 ohm. So in the same terminal, across the same terminal AB, we can connect back the load resistance which we removed earlier. So now the idea is, if you want to find out the current in 24 ohm branch, you can find out. If you want to find out the voltage across 24 ohm, you can find out. If you want to find out the current in 24 ohm branch, that is I24. For example, let me take that current in the 24 ohm branch will be I24. Let me want to find out the current in 24 ohm branch, that is I24. Then my formula, you know that the current formula, I is nothing but I is equals to V by R. So here the V is going to be VTH. So V by R. Here the V is nothing but our VTH, which is 8.57, and by R, if you take the total resistance of the circuit, where here you can see this 1.71 ohms and this 24 ohm, both are connected in series. Both the resistors are connected in series. So therefore, the total resistance will be, when resistances are connected in series, the total resistance will be sum of that. So therefore, if you sum it up, your 1.71 and 24 will give you some value. That is, you get the 25.71. So therefore, when you calculate your current, I is nothing but V by R. So if you calculate, you are getting 0.33 ampere. So this is the current flowing in 24 ohm branch, that is I24. Then after finding this I24, that is a current in 24 ohm, we can also, even if you want to find out the voltage across 24 ohm, that also we can do. So we know that V is equals to I into R. So we got the current I24 as 0.33. So into 24 will give you 7.9. So we know that V is nothing but I into R. So I, we got it as 0.33 into R value. R is nothing but 24 ohm here. So therefore 0.33 into 24 will give you 7.92. So this is the voltage across 24 ohm. So like this, we can calculate the current in the load resistor or the voltage across load resistor once we got the Thevenin's equivalent circuit. Thank you. Thank you all.